Next, let's do example 6 on page 639. But first, we need to look at something called the logistic equation. I have written it right here. Now, the logistic equation on the same page is something like this, okay? And as you can notice, that this is looks similar, but quite a bit different from what we're used to. That is, this part is the same as what we've been doing. That is y equal to a times e to the power kt, right? And then, however, but of course we have a 1 plus and then the whole c over it situation. The reason for that is because if you look at towards the top of the page, let's see, give me a second here, maybe this would be better. Yeah, it is. Okay, so if I show it to you this way, see, for this graph, if you have to plot this graph in the calculator or by hand, then it'll turn out to be like this. Now, the difference of this graph, which is called the logistic graph, is different from the regular exponential growth graph because it grows fast at first, right? But it reaches some kind of a turning point, a point of maximum growth, from which then it starts slowing down, which is more realistic. Because if you have a jar of, say, bacteria, as we have done in the previous example, and then you calculate its growth, it is true that in the beginning it grows in an exponential rate, but very soon it's gonna die down, okay? It's not gonna just grow, your 10 bacteria is not gonna grow out of there and take over the universe, okay? It doesn't work that way. It just, it'll grow fast for a while, but then it's gonna die down like this logistic graph shows, which is much more realistic. And in fact, if I have a box of bacteria and keep it in there, it'll probably be all dead soon. After some time. And anyway, and so the whole thing crashes. So anyway, the logistic graph is what we're gonna practice on next. Okay, so here's the equation. As you notice, it goes up, but then it tapers off into a leveling point. Another way of thinking that is, say, if you have a nice area that's good for deer, right? So you bring some deer and then you put it in the area. And at first, the deer grows very quickly, but very soon, then the predators also grow quickly and eat some of the deer, so the deer doesn't grow near as quickly as they used to. And eventually it reaches sort of a equilibrium, and that is what this graph is talking about. So let's look at an example 6. Which says that, let's consider some community, okay? The community has 1,000 people, and that's what the C is for. So I will write this down. We have a community, and it has 1,000 people who has the flu. And right now, at t equals to 0, there's only one guy in a community of 1,000 who has the flu. But we're gonna keep the community at only 1,000, okay? The community is not increasing. That is, we're calculating how many people have the flu, and the most that's gonna be is 1,000, okay? It's not gonna get any more than that, because there's only 1,000 people. So C then equals to, in this formula, then let's write down some information. First, C is given as 1,000. That's called the carrying capacity or something, or limiting, or, well, whatever, limiting value. All right. So next we need to, the next information is, and when t is 0, the answer is only 1. All right. And with that information, we can plug it in and figure out what A is. Because it says the function f, which is calculating in this example how many people have the flu. Okay, so f as 0 is only going to equal to 1, and that equals. So we'll plug 0 in here. Okay, and c is 1,000. So let's write that down. 1 plus. We don't know what a is yet, and then e to the power, e is just a number, right? 2.718, right? Or something. And then when t is 0, doesn't matter what b is. This whole thing is up there is going to be 0. So that is just a, right? Because e to the power 0 is 1. Everything to the power 0 is 1. And so that's 1 times a is a. So our formula becomes 1 equal to 1,000 over 1 plus a. 1 equals. I said 1 equal. Equal, please. All right. Now 1 equal to 1,000 divided by 1 plus a. Which means solving this equation, okay, that means move a up here, 1 plus a equal to 1,000, then a is equal to 999, and that's a for our formula, our logistic formula. So our formula, but we still don't know what b is, right? We know c, we know a, and we still need b for the formula. So let's keep reading. Well, b is given to us in this example. B is specifically referring to the growth of the flue is equal to a fixed number in this case. B equal to what? So B equal to 0.60 and 30. So that's B. So now we have the entire formula, okay? And the formula then is given as let me write that down. So our entire formula with all information given, that is f of t, which is the number of people who has flu or something like that, doesn't matter. The point is f of t equals to 1,000, c is given as 1,000, divided by 1 plus a is calculated at 999, and then e to the power minus b is that number right here, and 0.6030. Being that the book gave us that 0, so we'll write it down too, just to be nice or something. Anyway, so here's a t, and that is our formula for predicting in this town of 1,000 how many people's got the flu at any given time t. So any time t, like for example, say if you say t equal to 5, like 5 days or whatever, the t is in unit of. So 5 days later, how many people have the flu? Then you plug 5 in this thing right here, okay, and out comes some kind of answer. And okay, so let's see what do we want? Oh, we want to know how many people have the flu after 10 days. All right. And also, how many people have the flu if t becomes very, very big? Now, if yeah, but we'll worry about that. Let's see. Do we really need to care? We'll think about that later. Right now, let's figure out the 10-day business. To figure out 10 days, we will have, let's plug in the 10. T equals to 10 is, why did the book write it like that? Whatever, I don't care. So if, let's write it down here, okay? So at t equal to 10, that is f of 10 equal to, let's plug 10 in here with our calculator right now and see what comes of it. Let's see, so I will do it this way. Can you see it? Over here is good, right? All right, so we're gonna plug in that formula with t equals to 10. Having said that, I will, okay, we'll have 1,000, 000, divided by, okay, all that stuff, so parentheses, very important, divided by what? 1 plus 999 times e, where's e? Oh yeah, e is a shift situation. So shift natural log gives e, okay? Okay, so there's e, and e to the power, we'll put parentheses here just to be safe. E to the power negative, I have a negative sign here on my calculator. You might or might not. Negative 0.6. You can skip the 0, okay? It's 0.603. You don't have to type the 0 in. And then times t. T was what? Times, okay? T is 10. 10. Okay? Close parentheses, very important, close. And then another close parentheses because we're doing dividing, so there's a parentheses situation here. Otherwise, 1,000 will only be dividing by 1, and then you will get the wrong answer. Okay, so there's parentheses, and then I need to get out of there, get down. Okay, another parentheses, and that should do it. So let's see if I typed in everything right. I got 293, and then is that right? That sounds familiar. I think that is what the book said. Come on, move up. Can't find it. better put this down. Try again. 293.8. That is what I got, so that is correct. So that's what happens 10 days. Now, and the next question is, what happens after a lot of time has passed? In other words, if you graph this thing into the decimals calculator, right, and then look at this, what happens? Well, according to this model, then if you graph this in the calculator and zoom out a little bit, then eventually your calculator, you have to do the graph and reset the y-axis to like 1010. I mean 1100. Notice that the vertical line goes to 1100, whereas the horizontal line only goes to like about 26 or so. So you do need to pay attention to that. Okay. So according to this model, then the whole town is gonna catch the flu by the day 21. Does that really work that way? Don't know. Okay, I don't think during any flu epidemic that everybody catches it, but who knows? Maybe they do. I haven't really looked that much into it. It seems like, yeah, anytime when there's a flu season, only some of the people catch it and others don't. Like in my case, some flu seasons I catch the flu, sometimes I don't. Yeah, I just don't know why. So that is that. Okay, so now let's look at the next example. All right, example 7 on page 641. So example 7 on page 641, we are looking at a bunch of data, okay, and trying to figure out a graph that fits it. So let's look at the data. And if you look at the data, then you notice that the data is increasing quite fast in the beginning. Say from 1 to 2, it went from 0 to 1.3, and then from 2 to 3, it went up quite a bit less. And continually, as you go on, the increase become less. So so we have, now that we see this data, what kind of equation will fit this data? And that looks to me like some kind of logarithmic function, because as you might remember, logarithmic functions look this way. Okay, they go, here's a sample logarithmic function. It goes something like that. Okay, it takes a dive next to 0, and so it looks something like this, right? And we might have to at 1 it is 0. So yeah, so then so it's possible that it is a logarithmic function. So having said that, so it's just a wild guess, right? And having said that, we'll assume that it is a logarithmic function and see what happens. It could also be other functions as well, right? But right now we're doing logarithmic functions, so that's be our most obvious guess. So let's assume that this is some kind of logarithmic function, a simple one, where y equals to we'll assume that it is y equals to a times natural log of x. It's just a guess, okay? Why natural log? Everybody likes the natural log. Nobody used the other one. And anyway, so having said that, then what about it? So then, and then we'll try to fit this information in there to see if it works. Then we'll know what a is, okay? To check to see how our guess works out. So let's say it's y equal to a natural log of x, and then we'll pick a piece of data to calculate what a might be, and we'll pick the number 9, the last one. Okay, it says right here when x is 9, y is 4. Excuse me, 4 point whatever. Okay, so we'll pick that number and write it in. So when x is 9, natural log of 9, y equals to 4 point whatever, 4.394, right? Okay, and with that information, we'll calculate a. Then a then equals to this thing divided by that, okay, and which is whatever. And let's actually right. So then our formula will be that what I just said. Y equals to a, which is natural log of 9, divided by 4 point something 394. Right. and then times, this is just a number, okay? This looks complicated, but it just takes you a few seconds to punch this out in the calculator. And then that equals the natural log of x. Remember, this is, a is, oh man, I wrote it upside down, didn't I? Now I have to erase it. Okay, try then. A equals that divided by that, okay? So 4.394 divided by the natural log of 9. That's much better. So then we will plot this thing into the calculator, the graphics calculator, and that will give us the result. But first, let's punch this out. Where is it? Okay, right here. All right, so I stand a little closer. We have, let me clear this. We're just doing the 4.394 divided by natural log. So I have 394, right? Okay. Divided by natural log. Where's my natural log? There it is, 9. Close parentheses. And that equals 1.999. Okay, so we'll take that as 2. So yeah, so we'll just plot the 2, and I plotted this thing into the Desmos graphics calculator to show you how this is done. Please do this yourself as well if you can. Okay, let me load the graph. Come on, move faster. Okay, give me a second here. I have to stabilize it. So here we go. That is here's what I plotted into the Desmos calculator. Let me make it a bit bigger. Okay, that should do it. Okay, now please do this yourself as well. Okay, first let's plot the dots in the calculator. So here are the dots. To plot a dot into the calculator, the Desmos calculator, I'll have the link in the video description below. You type parentheses, the first coordinate, and comma, and then the second coordinate, and then close parentheses. So I have a bunch of dots here that you can see as a sample. And when you do that, then you get all these dots just like the book did. Okay, I don't have all the dots here. The rest are up there, okay, which I can't show, but you get the idea. You just type all of them in, and it doesn't matter which order, and then you type in the equation, which we have is y equal to 2 natural log of x. Now the Desmos calculator has a button here. These things here, they are buttons. They're not just decorations. If you click it, it blanks out. See? So you don't see the y equal to 2 natural log of x. If you click it, then it'll kick in the graph so that it looks like this. And so let me shrink this a little bit. Okay, that's good. See, so if you click it, then the graph will show up. See, that graph is y equal to the natural log of x. And as you can see, it's a pretty good approximation of the original dots. And also the book gave a lot of decimal points for the dots. Right? It's not just 3.6, it's 3.6 and 2 more digits, which I didn't bother to type in. And that's why my graph isn't as accurate. You notice my points are not perfectly on the red line, and whereas the book's is actually perfectly on because the book typed in 2 more decimal points, which I don't want to bother. But this is more realistic, see? In real life, when you approximate a bunch of points, it's extremely unlikely that your graph is just going through it so perfectly. Well, unless you designed it more than a more complicated graph than just doing the natural log. But anyway, so here we are. This is how you do this thing. So please do this yourself in the Desmos calculator. Okay, as long as you do this in there, you should not have a problem with it. And you can type in just 1 decimal point like I did, or type in all of them so that you become more perfect. And your choice. So that is example 7. And next, we need to, let me get back. Next, let's look at page 642, where the book just want to make a quick mention. Now, y equal to 2 times natural log of x, by the rule by the power rule that we mentioned, okay, you can kick the m up on top here. That is, this should be the same as y equal to natural log of x squared, okay, because the 2 can go up here if they want. They're the same thing. So to show that, we have the book has graphed both things. As you can see, the top one is y equal to 2 natural log of x. The bottom one, y equal to natural log of x squared. They are the same because this formula says so. Okay, so that is that. And next, let's look at the next example, example 8. Example 8 says we need to pull off some kind of a trick. Okay, example 8 we have in the following page. Then y equal to 2.5 times 3.1 to the power x, and we need it to look like this because we like this thing and we want everything to look like it. Okay, so let's do that. Let me write this down. So example 8, we have y equal to 2.5 times 3.1 to the power x. Now what's wrong with that? Nothing. However, we like this thing, okay, and we want everything to look that way if possible. So we're going to pull a trick, and so the goal is make this look like that. And how's that going to happen? Well, we are going to, let me see, so y equals 2, okay, let's write that down. And then mostly we need to work on this part. I don't think that matters as much, but we'll see. Equal to 2.5, okay? And what is that? We are going to take the natural log of this thing. So we'll take the natural log. So it'll be, if we take the natural log of this thing, it'll be natural log of 3.1, okay, with the x written in front, right? So that is the natural log of this thing. And then we'll write down the e in there, and that will be, that's about it. I think I went a bit too hurried to it for the explanation. So let me explain a little further. So what we're gonna do is let this thing, we'll take the and let this equal to something. Okay, what we're gonna do is called y equal to 2.5 times, what do we call this? Let's call it w, okay? Where w equals to 3.1 to the power x. And we want to change w to look like this part. It has an e in it. So to do that, what we're going to do is first we'll take natural log of w, okay? That equals the natural log of 3.1x. Okay, and then secondly, this will be equal to, we'll kick the x in front according to this formula right here. Okay, kick it in front, and that will be equal to natural log, x is now in front of natural log, 3.1, all right? And then next we have, and then that's natural log of w. So then w itself, we'll write a giant E under it. So this is natural log of w. If we write down a E down here, okay, write down E, and this value, E and natural log will cancel themselves out, just like like this one, okay, b and log base b cancel themselves out, so the left with just the stuff inside. So similarly, this thing is the same as w, because e and natural log cancels out. So then w is equal to e to the power x natural log of 3.1, which is what I wrote here, and that is the answer. Okay, what we're shooting for in this problem. All right, so that is what you do if you ever look at this and decide, I don't like the look of it, I want it to look that way. So if you're picky like that, then that's what you got. So basically, you just slap, basically how you do it is you slap an E underneath it, and then slap a natural log in here. So because E and natural log cancels themselves out, so you get that thing back if you want. So so that's that. Let's see. Yeah, that looks about right. Okay, so that's example 8, and I think we have come to the end of this section. All right, so the homework is on page 647. because there are a lot of blank pages here. All right, so then let me see. Give me a second here. So homework on page 646, please do problems 13, 19, 21, 23, 25, 27, 29, 31, 33, 35, 37, 39, 41, 45, 47, 49, 51, and 53. Now that sounds like a lot of problems, but it's worth it, okay? Logarithmic practice problems, to me, very interesting, okay? Watching a bacteria grow or die, either way, and some chemical decaying or something like, some deer population, flu population, or some other population. So, and it's more interesting to me. So I believe they're worth doing for the fun of it, okay? It has a much more fun factor, and it's also something that you don't see every day. And most of the time, the proportional, the regular straight line, increase, decrease. I mean, anybody knows how to do that, more or less. Because you know, say if two kids needs 4 oranges, how many oranges does 10 kids need? Well, everybody knows that. Whereas this formula is a little more tricky and interesting and stuff, and is also to simulate real life. So please do your homework, and when you're done, I want to talk about some of them. Okay, next let's look at problem 19 on page 647, where some fish population is represented by this particular formula, which is the logistic formula right here. Okay, so let's figure out what they want. Okay, what are they asking? Problem 19 says, what is the doubling time? I assume that means when the fish population doubled, I guess. Anyway, let's try it, see if I'm right. Okay, so first we need to figure out what P0 is, right? So what is how many fish is there in there when time is 0? And then after that, then we'll figure out what time it takes for this amount to double. So P of 0 is, pop this as 0, e to the power 0 is 1, so it's 1,000 divided by 1 plus 9. That's 10. 1,000 divided by 10 is 100. So P of 0 is just 100. All right. So to double it, it will be 200, right? So then we'll put it in this formula. So if we have 200 fish, 200, that's a 2 here, 2, and 200 fish, and then what would T be? Okay, that would be equal to 1,000 divided by this 1 plus 9 e to the power minus 0.6 t. All right, so now we just have to solve for t, and then we know how much time has gone by to double this thing. And so in other words, we need to solve this equation. We're gonna push this thing up here and push the 200 down here. Then and that would be 1 plus 9 e to the power minus 0.6 t is going to be equal to 1,000 divided by 200, which is 5. Okay, and then e to the minus 0.6 t is going to be equal to 5 minus 1, okay, which is 4, divided by 9, and then and keep going. That we have to get rid of the e, we take the natural log of both sides, which will give negative 0.6 t equal to natural log of 4 over 9 in parentheses. And then finally, t equals to 4 over 9 divided by negative 0.6, and which is what we're going to do right now. Okay, so t equal to whatever. And let's figure that out. Okay, so I stand over here. I'll turn on my calculator, and let's do this. And natural log of, let's see, can you see it okay? Yeah, it looks okay to me. Okay, natural log, anyway, natural log of 4 over 9, 4 divided by 9, close parentheses, divided by negative 0.6. 0.6, that should be equal to t, and I get 1.35. So after 1.35, then the thing will be doubled. Okay, 1.35, is that right? Let me check the answer here. Problem 19, 1.35. Yeah, it says 1.4 years. So good enough. Okay, so that is the answer to problem 19. Next, let's go to problem 23, which I did not write it down. That's okay, I guess. Let me write it down. So now we are going back to this formula right here, okay, without the green part. The green part is for the cooling temperature things. So just this part, the black part, and as something has a half-life of 2,000 some minutes, all right, we'll keep that in mind. If the initial amount was 132.8 grams, so A0, that's the A here, I'll write down A0. 0 means initial. Okay, initial amount is 132, so we have y equal to 132 grams, and then 0.8. What? 0.8. Okay, let's not forget the 0.8. Okay, 132.8 grams. And then how many half-lives will have passed before the substance decays to 8.3 grams? So after some time, then this thing has turned into 8.3. So it really went downhill, right? It went to 100 something to only 8. 8.3. And that will be equal to this thing times e to the power k of t. Let's see, okay. All right, now to figure out what k is, we are going to use the half-life information. That is, this thing, the same formula, okay, times 8, is going to be equal to half this much. That is 138.32.8 divided by 2. That's the second equation. When it has gone to, let's see, that also equal to e to the k of t. The half-life is, and it's not just t though. We do know what t is because it gave us the half-life. So in other words, after 2,000 some minutes, this stuff is only going to be half as much. All right, so t equal to 2,000 and something, 2045. Now from this part, then we can figure out what k is. And once we figure out what k is, then we can figure out what t is. All right, so then let's figure out what k is. What is k? K is equal to, these two numbers cancel out, okay? The A0s cancel out anyway. So k is equal to, so that left 1/2. We'll take the natural log of both sides. So natural log of 1/2, and then that will knock out the e, and then we'll divide it by 2045, and then that will leave just k here. Okay, now I did all that a bit fast, but what we're doing is first take the natural log of both sides. So there's a natural log here, which cancels out the e. So we have only k times this thing left. And second step, I move the 2000 to the 45 to the other side, so we'll only have k left. Okay, so this is the same thing we've been doing in the homework as well. So that is the value of k. Whatever that is, then what were we doing? We are trying to solve for, let me see what we're doing. Okay, and so they're asking how much time has passed that before, how many, it specifically says how many half-lives, but we'll worry about that later, okay? So let's say how much time has passed. We're going to solve for t in this equation when we already know what k is, see? So then to solve for t, then we have to write down the formula is, all right, to get t out of this formula right here, okay, we'll take the 8.3, all right, and divide by this number, divide by 132.8, and then that just have the e here. We'll get rid of the e by doing the natural log, okay, that will get rid of the e. The whole thing is in parentheses, and then we have only k and t left. And then if we're looking for t, so let's divide it by k. Okay, divide by that. Divide by k, where k is this thing. And if we do that, then we will have our time of however many minutes. Whatever this is, minutes or something, days, years, doesn't matter. But if we do that, then we should be able to get the right answer. And to do that, let's punch it into the calculator, okay? Okay, so here's my calculator. that looks kind of complicated, but it's not. As long as you do it systematically, everything should come out. So we have natural log. Okay, start with natural log of it already has parentheses of 8.3 divided by 132.8 close parentheses. So far so good. We got that thing on top. Divided by what's on the bottom, k, we need to put it in parentheses, okay, just to be sure, so that nothing's confused. So that this, being that it's being divided, yeah, let's put it in parentheses. And so parentheses divided by k. So k is natural log again, as 1/2, which is just 0.5. So I'm just going to type in 0.5. Okay, close parentheses. That's the parentheses for the natural log only. And then divided by that number, where's division? 2045, 2045 divided, right? Yeah, that looks okay. And then close parentheses, and that should do it, okay? Let's see if I got it right. That equals to something, 8180. So t equals to 8180. All right, so that's so far so good, but let's see what they want. What was the question again? Let's find the question. The question is how many half-lives? Okay, in other words, each half-life is 2045, and how many is that? If one unit is 2045, so how many half-lives? Let's call it HL. Okay, HL is equal to this divided by that. So that will tell us how many half-life. If each half-life is 2000, right, something, and we made it through 8000, so how many 2000 something is in 8000 something? So do the division, 2045, right? That should give us how many half-lives what is the total time of decay? The total time would be this, right? But how many half-lives? Let's do the division. So I got the two, I already have that still in there. So let's just push divided by 2045. Yeah, that's about it. Push answer, and it equals to 4. Okay, so 4 half-lives has elapsed. What are the 2000 means what? Minutes. Okay, so that is so 4 half-lives or 8000 some minutes should be the answer. Now, so let's look at answer to this thing. 23. 4 half-lives. It says 8.18 minutes. What does that mean? Let me think about it. Oh, the reason it says 8.1 is because I read this problem wrong. It's not 2000 minutes. It's 2.045 minutes. So there's that changes nothing. Okay, it's everything's the same. We just need to add the points here. So then, yeah. So the total life is 8 point some minutes instead of 8000 minutes. As one's as good as another to us, anyway. Okay, so that is problem 23. Okay, problem next, let's consider problem 25, where m equals to blah, blah, blah log s 0. Now, what we're trying to do here is we need to figure out what s is. You know, pull everything else out of there and throw it to the other side of the equation. That way it'll give us a formula for calculating s. Now, you might ask, what is m and what's s? We don't care, okay? Not right now. Right now, we only care about how to throw them all on the other side, and we're done. So to do that is, first, we can get rid of this, easy enough. That would be 3m divided by 2, okay? Lift the 3 up, push the 2 down. The division line. So far so good. Then we need to get rid of the log. To get rid of the log, we need, without no numbers means base 10, we just put a giant B under it, okay? So then, to get rid of that, to cancel out the log, we need to put a giant 10 down here. So 10 to this power, I'll put it in parentheses. And so that got rid of the log. And finally, we need to, s is dividing by something, so we need to multiply. So this whole thing is multiplied by s0. And that equal to s is the formula for what we're shooting for. That's about it. Okay, so let me look at problem 25. S equal to S0 times S0 times 10 to the power 3m over 2. That's it, see? And that's problem 25. Next. So problem 27, we're supposed to show that b to the power x is the same as e to the power x ln b, which is something we did before, but we'll do it again, okay? And so to do that, we will, let me see, first we will, we'll take the natural log of both sides. That is ln of b, taking natural log of both sides, equal to ln of e, which cancels out, so you got x ln of b left, and which is yeah, whatever. And then finally, and let me think, okay? I think I'm spinning in circles. Doesn't matter, it's circles anyway. Then the next step is we need to write down a giant E down here, and then so then this side looks just like that, and this side, e and ln cancels out. It goes back to b to the power x. That's good enough. Let's look at the next problem.